This is going to be another thermo video, and in this video we're going to be covering steady flow open system devices. We're going to be going over an example from the book. This is from chapter 5, example number 46, and I'm going to read the question real quick. So it says steam flows steadily through an adiabatic turbine. The inlet conditions of the steam are 4 MPa, 500 degrees Celsius, and 80 meters per second, and the exit conditions are 30 MPa, 92% quality, and 50 meters per second. The mass flow rate of the steam is 12 kilograms per second. Determine A, the change in kinetic energy, B, the power output, and C, the turbine inlet area. Okay, so one thing that I like to do to start off any problem in thermo is I like to write our assumptions down. Okay, so what can we assume here? Well, it's telling us in the first sentence that we have an adiabatic turbine. So we can say that the Q dot, the heat transfer, is 0. And being that this is a turbine, as you recall from the other video going over all the different kinds of devices we may experience in thermo, we see that for turbines, the change in potential energy is negligible. So we can say the same here. Okay, and I believe that's all we can assume for this. So another thing I like to do is I just like to write down what we're trying to find. So in this case, I'll just underline it. Change in kinetic energy. So change in kinetic energy. Power output. And then the turbine inlet area. So we can call A1. So this is what we need. All right. Now from here, I like to start with a mass balance. So for this case, we just have the inlet 1, mass flow rate of the inlet 1 would equal mass flow rate of the inlet 2, since there's only one inlet and one outlet. So this is pretty simple. We just know the m dot for both is going to be 12 kilograms per second. That was given to us. Okay. So for part A, we want the change in kinetic energy. So let's break this down. Okay, let's do green here. So A. So the change in kinetic energy we know is 1/2 mv squared. And if we write it in terms per unit second, we have 1/2 m dot v squared. So we can say that the change in kinetic energy would be 1/2 m dot of your final v final squared minus 1/2 m dot initial v initial squared. That is equal to change in kinetic energy. So we're given all these quantities. We know m dots are both 12 kilograms per second. V2 is 50, it's given to us, squared, minus 1/2, 12 kilograms per second. And V1, also given to us, 80 meters per second. Okay, so if we evaluate that, I'm just going to save the effort and tell you what it is. The change in kinetic energy is equal to 1950 joules per kilogram. That's negative, or negative 1.95 kilojoules per kilogram. So the reason this is negative is, of course, because we're dealing with a velocity that's greater at the inlet than at the outlet, meaning that our kinetic energy will be smaller at the exit than at the inlet because the m dots are the same and the v's is different. Okay, so then this is our part A. Okay, now we can move on to part B. So part B asks for the power output. So W dot. And another thing I usually always do with thermal questions is I always do an energy balance. So let's write that here. Okay. So the general form of the energy balance is Q in plus W in plus M dot H1 plus V squared over 2, 1 plus GZ1 equals Q out plus W out plus M dot H2 plus V2 squared over 2 plus GC2. All right. And since this is a turbine, we know turbines produce power. So we could say that W in, the work in, that is equal to 0. So I guess that would be one of our assumptions that we did not include up here. Say that work in is equal to 0. Okay. So now let's start evaluating this. We said Q is 0. Sorry, I forgot the dot. We said Q is 0 from our assumptions earlier. W in is 0. And then we can actually evaluate this. So we're trying to find W out. Okay, so M dot, we know M dot is 12 kilograms per second. H1 we don't know, so let's leave it as an unknown for now. V1, 80 meters per second squared for 2, and this is negligible, we said. Potential energies are negligible. So it's equal to W out plus 12 kilograms per second, H2 plus V2 squared over 2. Well, let's plug in V2 squared actually. V2 is 50, so 50 squared over 2 meters per second, of course. Okay. So now let's find H1 and H2. Okay, so let's start with H1. So H1 we know is, well, we know the temperature and pressure for H1. So right away, looking at our saturation tables, we see that at 4 MPa our temperature is greater. Our 500 degrees Celsius, is greater than the saturated temperature at 4 MPa. So this means that it is a superheated vapor, which obviously we know because it's a steam here. So we would look at table A6. So let's write that here. So table A6, and we go to 4 MPa as well as 500 degrees Celsius, and H1 is right there in the table, and that value is 3,446 kilojoules per kilogram. All right. And then for H2, we know at the outlet, We know the quality is 0.92, so we can use the quality equation. So 0.92 equals H2 minus HF over Hg minus HF. Okay, and now looking at table A5, we can find the HF and Hg that correspond to 30 kPa at the saturation table. Excuse me. Okay, so if we go ahead and do that, we get values of approximately, for HF at least, we get 289.27. Hg, we get 2624.6. Okay, so if we evaluate that out and do the algebra, we get H2 is about 2437.77. And of course, this is kilojoules per kilogram. All right. So substituting those back in our energy balance equation. So what I'm going to do here actually is I'm going to move this term right here to the other side. So since 12 kilograms per second is multiplied by those, we can just factor that out. So we get H1 minus H2, and then plus 80 squared over 2 minus 50 squared over 2. That's all equal to work out. Okay, so if we plug in our H1 and H2, and then evaluating this term out, 1950. So recall before I proceed, this right now is in kilojoules per kilogram. Okay, and this term, our velocity term, is usually just in joules per kilogram by default, just the way it is. So we have to get these units the same. So since this right now is in joules per kilogram, we have to multiply this by 10 to the minus 3 to get the whole term in kilojoules per kilogram. Okay, so doing that and solving this out, we get that the work out, or the power out, I should say, is 12,122.2 kilowatts, or we can say that's 12.122 megawatts. Either one is fine. So that's part B. Okay. And now moving on to part C. So I'll bring the question down in case we forgot. Okay. So for part C here, we need the turbine inlet area. Okay, so one equation that I know for sure that we can obtain area from is the mass flow rate equation. So we know that mass flow rate is rho VA. Of course, since it's an inlet area, these are all inlets. And we know m dot, which is 12 kilograms per second. Rho 1, we don't know. So we'll leave that as an unknown for now. Velocity 1, obviously, is 80 meters per second. And then obviously we're trying to find A1. So the question is, how do we get this rho 1? So what we can do here actually is we know the pressure initially and we know the temperature initially. So really we could find the pressure, the density. And the way we can approach that is we can use the ideal gas law. So as long as we can treat steam as an ideal gas for this case, we can go ahead and do this. So rewriting the ideal gas law, it's usually PV equals nRT. But all I'm going to do here is write it in terms of density. So pressure equals rho RT. So these are the same equation, really. All right. So using this equation down here, we know the pressure initially is 4 MPa. So let's just write everything in pascals. The density 1 we're trying to find, R1. So that's the specific gas constant of steam. So we actually have tables for this. So if you go to table A2 in your book, you can get that the constant for steam at 4 MPa and 500 degrees Celsius is 461.5 joules per kilogram Kelvin. Okay, or 61.5 joules per kilogram Kelvin. And then finally T1. So T1 we know is 500 degrees Celsius. Converting that to Kelvin, we just add 273. So we get 7, or I'm sorry, let's redo that. So 500 degrees Celsius, to get it to Kelvin, at 273.15. So we get 773.15 Kelvin. Okay, and then if we solve for rho, you get that rho 1, or rho of the steam, is 11.215 kilojoules per meters cubed. I'm sorry, that's not our final answer. So from here, now we can just substitute it back in our original equation. So throw this back in there. We get 12 kilograms per second, 11.215, 80, right? So getting A1, we get a value of approximately 0.0133 meters squared. Hope you guys enjoyed.